forces acting in a mechanism, right? Forces acting in a mechanism. So we'll take an example of a 4-bar mechanism, right? We have links like DA, AB, BC, and DC. Right? Here DC is a fixed link, and BA is acting on link A, which is rotating with the velocity omega A. Similar way, BB is acting on point B, right, which is moving with an angular velocity omega B, right? And there are two forces. FB is acting along the side of BB. FA is acting along the way of BA, right? So which means force A and velocity A are on same direction. Similar way, force B and velocity B are of same direction. Right. Now we will fix them in the equation. Input work is equal to output work if there is no any loss of energy. Right. So my input work is force into velocity. Right. The unit of force in the unit of velocity will give you the work. Right. Therefore, FA into VA, right? FA into VA, the velocity of A, will be equal to, this is the output, right? So if this is my input, the moment of this would be the output. So that is FB into VB, right? FB into VB. From this, I can find what this FB is if I know other three factors. So FB is equal to FAVA upon VB, right? FAVA upon VB. If we consider the effect of friction, so this is an ideal equation. If there is no friction, no energy loss, nothing, this is the equation. If we consider the effect of friction and assuming the efficiency of transmission as n, neta, right? The efficiency, we usually note it as neta. Then neta is equal to output upon input. The efficiency is equal to output upon input. So output is FB into VB, right? Input is FA into VA, right? FA into VA. So from this you can find FB, right? FB is equal to neta into FAVA upon VB, right? Neta into FAVA upon VB will give you the FB. If the turning couples due to the forces FA and FB about B and C are denoted by tau A, right? TA, right? Known as driving torque. Then these equations can be written as TA omega A equal to TB omega B, that is tau A omega A, angular velocity A will be equal to tau B into angular velocity B. Then efficiency will be known as TB omega B upon TA omega A, that is output upon input, that is TB omega B upon TA omega B, and this tau T and omega is angular velocity, where omega A and omega B are the angular velocities of the links DA and TB respectively. So if you have the values of F and V, you can go for this equation, FBVB upon FBA. Or if you have the values of tau and omega, tau and angle, then you have to go for this equation, right? If the forces FA and FB do not act in the direction of the velocities, right? So here you see VA is acting this way and force A is also acting this way. So the line of action of force and velocity are same. Okay. Here also FB is acting this way and BB is also acting the same way. So the line of action of V and F are same. Right. In case if they do not act in the same direction, right? If they do not act in the same direction of the velocities of the points A and B respectively, then the component of the force in the direction of the velocity should be used in the above equations. So say for example, my FA is acting some other direction of VA and FB is acting some other direction of VB, right? Then my force component which is on that particular direction will be considered. I will draw like simple 4-bar mechanism, right? So 4-bar mechanism. Okay. My VA is anyhow going to act this way. This is point A, and VB is anyhow acting this way. Right? Why? My link is here. Velocity should be perpendicular. So this should act that way. And my link is here. Velocity should act perpendicular. So this is my VA. And say for example, I have a force FA acting this way, and the force FB acting this way. Right? This is my FB and that is my FA. So when considering the forces acting in such a way, we need to go for the components of this, right? If I consider this angle as alpha, you know, the force component which is acting this way is Fa cos alpha, right? Fa cos alpha. And the component which is acting this way, that is Fa sin alpha. I have nothing to do with the Fa sin alpha because that is perpendicular. I can't do, right? I will go for the Fa cos alpha while putting it in the equation, right? So now Fa cos alpha into velocity A will be equal to, again, this. I take this as angle beta, right? So this is going to be Fb cos beta, right? Component of force which is on the direction with the Vb is Fb cos beta, right? So Fb cos beta into Vb, right? So this is your input and this is your output. You know, beta is equal to output upon input. So my output is Fb cos beta into Vb, and my input is Fa cos alpha to Va. Okay. So this is your beta. Beta is equal to Fb cos beta into Vb upon Fa cos alpha into Va. Right. So only the component of the force factor will be applied on this equation. Right. So this is for the forces which are not acting on the direction of the velocity. Okay. It is always not necessary the force and the velocity should be in same direction. Right. They may act on the different way also. Right. So this is how we find the force acting in the mechanism in a different way. Then we have mechanical advantage, right? Mechanical advantage is noted as MA, right? Mechanical advantage MA. Ideal mechanical advantage is equal to FB upon FA, right? FB upon FA. So FB is the output force and FA is the input force, right? And if I write it in the form of velocity, then that would be equal to VA upon VB, right? Why? Because you know FA is equal to FPVB, right? FA VA equal to FB VB. So if mechanical advantage is equal to V upon VFA, that is output force upon input force. So FB upon FA, which means VA upon VB, right? So which can be written as VA upon VB. All right. If we consider the effort of friction, right? This is for ideal gas. What I have written here is for ideal gas. There is no friction, so there is complete energy transfer, right? In case if I have friction, then we have to go for the efficiency meter, so that will accommodate the loss of energy, right? So mechanical advantage, actual, right? So this is ideal, right? This is ideal mechanical advantage. So actual mechanical advantage, you need to multiply the actual with the neta, right? So neta into ideal, right? Neta into ideal will give you the actual. So neta into mechanical advantage ideal will give you the actual mechanical advantage. I can write it as mechanical advantage A, that is actual. So when you put it in the equation also, we will have a neta here, we will have a neta here, right? Neta is the efficiency, right? So if I have F and V, I can go with this equation. If I have only tau and omega, then we can go with the another equation also, right? The mechanical advantage may also be defined as the ratio of output tau to the input tau, right? So this is output velocity to, so not velocity, output force to the input force, right? We can write in respect to output tau upon input tau also, right? So that is tau B upon tau A, that is omega A upon omega B, right? So ideal mechanical advantage is going to be tau B upon tau A, which will be equal to tau omega A upon omega B, or, and actual mechanical advantage, you need to multiply it with neta, right? Neta into tau B upon tau A equal to neta upon omega A upon omega B, right? So this is how we find the mechanical advantage, right?
The Hoba mechanism has the following dimensions. Dimensions are given. DA is 300 millimeter, CB and AB are 360 millimeters, DC is 600 millimeter. The link DC is fixed, and the angle ADC is 60. The driving link DA rotates uniformly at a speed of 100 rpm clockwise, and the constant driving torque has the magnitude of 50 Newton meter. Determine the velocity of the point B and angular velocity of the driven link CB. Also find the actual mechanical advantage and the resisting torque if the efficiency of the mechanism is 70%. Right? So we'll put this given data into picture. Right? So DA is given 300 millimeter and CB and AB are 360 millimeter. CB equal AB equal 360. Driving in DA rotates at 100 rpm. DA rotates at 100 rpm clockwise, right? Clockwise direction. Tau of driving is equal to 50 Newton meter, right? 50 Newton meter. Now what we have to do is velocity of the point B. We have to find the velocity of point B and angular velocity of the ribbon link CB. Angular velocity of the CB. Also find the actual mechanical advantage, right? Mechanical advantage, actual, and also resisting torque if the efficiency of the mechanism is 70%. Right? 70% advantage, resisting torque. So these all are the given data, and these all we have to find, right? Okay, so as usual, we'll draw the diagram, right? I will go for a scale factor of 600 millimeters equal to 12 centimeter. All right. So this is our DC, right? DC. Then I have DA is rotating at 100 rpm, and DA is equal to 100 millimeter, right? Not 100, 300 millimeter. So if my 600 millimeter is 12 centimeter, 300 millimeter is equal to 6 centimeter, right? So on 6 centimeter, I will draw an arc, right? I will draw an arc. So 1, 2, 3, 4, 5, 6. In my 6 centimeter, I will draw an arc. CB and AB are 360 millimeters, right? So CB, that's going to be somewhere here, and AB, that is going to be somewhere here, right? That is 360 millimeter. Okay. So as a rough diagram, right? 360 means 18, right? Not 18. 7.2. According to my scale factor, 600 mean 12, 300 mean 6, and 360 mean 7.2 centimeter. I need to draw an arc, right? 7.2. Okay. So since I don't have any protector on this, I will randomly draw an arc. Okay. So the diagram is going to be something like this, right? Draw according to the scale, right? That's why I put all the scale factors here, right? Draw according to the scale. But now in the screen, I couldn't find a protector, right? So this is how our diagram is going to be, right? So now I will explain with what I have already drawn, right? So here I have CD, right? CD is equal to 600 millimeter, right? So CD, this is 600 millimeter, and DA that is 300 millimeter. CB and AB are 360. CB and AB, these are 360, right? And this is rotating with an angular velocity of 100 rpm. Okay. So now we'll see how to draw the vector diagram, right? Vector velocity diagram. We know velocity is always perpendicular to the link, right? So if dA link is this way, the velocity is going to be perpendicular to that in this way, right? So I will have a perpendicular along this way. All right. So this is going to be my VA, since D and A are DA should be perpendicular to VA. Then C and D are fixed points, right? So I will draw CDA parallel to this with some scale factor, right? For certain scale. Then, right, I have a line AB, right? That's line AB. So the vector for this is going to be something like this, right? Either this way or this way, it's going to be. Similar ratio for CB, the velocity is going to be in this direction, right? So now we have to fix them in the velocity diagram, right? Okay, so according to given data, the AD is rotating with 100 rpm, right? So we know 100 rpm can be converted into omega, that is 2 pi into 100 by 60, that is equal to 10.47 rad per second, right? That's given here, right? 10.47 rad per second. Now we are drawing the velocity diagram, right? But what I have is the angular velocity, right? From angular velocity, I need to go for the velocity. So that is, we need to divide the angular velocity with the velocity. So V is equal to omega is equal to V upon R, right? Omega is equal to V upon R, which means V is equal to omega into R. My omega is 10.47 rad per second into radius. So radius of this dA is given 300 millimeter, right? 300, this is 600, this is 360, and this is 360. Okay. So this is given 300 millimeter. That is 0.3 meter. Okay. So this will give you 10.47 into 0.3, that will give you 3.14 meter per second. Right? So based on the given data, I found the angular velocity, I find the velocity. Right? Now I am going to apply this in the velocity diagram, right? So according to velocity diagram, say for example, I will take like 3.14 meter per second as 6.28 centimeter. Okay. Say for example, this is our scale factor, right? So for 3.41 meter, 14 meter, I will take as 6.28 centimeter, right? So my AD, right? This is our AD that is equal to 6.28 centimeter according to what the scale I have taken, right? Then I need to draw any one of these lines, right? Since C is a fixed line, it's a fixed point, C is also going to be near to the D, right? So from there, perpendicular, that is this one, we need to draw same here, right? We don't know the length, we'll just draw it, okay? So this and this should be parallel. Similar way, for this line, which one? CB, right? So CB, I will draw parallel to this, right? So this is going to be my CB, not CBAB, right? And this line will meet at a point, okay? So this point would be the third point B, right? So what I have got is the velocity triangle, okay? This is the velocity triangle. What we have to do now, our question is determine the velocity of the point B and angular velocity of the driven link CB, right? So we can measure this, right? We can measure this and multiply by the scale factor. We will find the length of this, right? And thereby we will find the velocity of the point also, right? Now we'll see, since the link BC is fixed, right? This link BC is fixed. Therefore, the point B and C are taken as 1 point, right? That's why B and C are taken as 1 point. Draw vector DA perpendicular to DA, right? So vector DA, right, which is drawn here, this is perpendicular to DA. This is perpendicular to DA to some suitable scale. So this scale you need to decide, right? And similar way, you have to write the scale as well to represent the velocity of A with respect to D, or simply velocity A. Since D is a fixed point, only this is moving. So velocity of A with respect to D, okay, that is 3.14 meter per second, right? That's not 2. All right. Now from point A, this is point A, this is point A. Okay. Draw a vector AB perpendicular to AB. Right? AB, draw a vector perpendicular to AB, and this are going to be parallel, right? So this and this should be parallel. To represent the velocity B with respect to A, right? Velocity of B with respect to A will be denoted by this line. And from point C, draw a vector CB perpendicular to capital CB. So this is our CB. The line perpendicular to that will be this line. So this is known as velocity of B with respect to C, right? C is a fixed point. So velocity of B with respect to C, right? Vectors AB and CB intersect at AB. So the point of intersection of these two is the point B, right? By measurement, we find the velocity of point B. BB is equal to BBC is equal to vector CB. With vector CB. So this is a vector. By measurement, we find it as 2.25 meter per second. So you will have some value in like some centimeter into your scale factor. You will have the velocity, right? So don't just measure and write measurement into the scale factor. All right. And then angular velocity of the driven link CB. So angular velocity of this link is also asked, right? So we know BBC is equal to 2.25 meter. So omega is equal to B upon R, right? B is given 2.25 meter, right? And R is 0.36. BC, you know, this is 0.36, right? That is 0.36. So when you divide this, you will have 6.28 rad per second, right? Actual mechanical advantage. We know that the efficiency of the mechanism is equal to 0.7. It's given 70% advantage, 70% efficiency, right? So it means eta is equal to 0.7. So actual mechanical advantage is equal to eta into omega A upon omega B, right? That is angular velocity of output over input. So omega A is found as 10.47 rad per second at the start of the question. Omega B, that is the driven length, that is found as 6.25 rad per second. So at the end, we will have 1.17 as the mechanical advantage. Since this is also radian per second, this is also radian per second, mechanical advantage will not have any time, unit, right? There's no unit for it. Then the question is asked, resisting torque. Resisting torque. Torque equation we know, eta is equal to tau B omega B upon tau A omega A. Tau B omega B upon tau A omega A. This tau A and tau B are, this is output, this is input, right? So when you substitute all the values you know, right? Omega B you have already found 6.25, right? Omega A you already found 10.47. Tau A that is given 50, right? That is given 50 in the question. So based on that, you can find the value of tau B, that is 58.3 Newton meter, right? 58.3 Newton meter. So this is how we found the mechanical advantage and resisting torque.